Welcome to Daily Papers, the podcast where we break down the latest and most interesting academic papers into something you can actually understand. So we all use AI now, right? We ask it for recipes, to help with our homework, to write emails.
It's everywhere, and it's incredibly powerful. But it has this one very strange, very big problem. Sometimes it just makes things up.
Right, it lies. But it does it with such confidence. You could ask it, who was the first astronaut to bake a cake on the moon? And it might spit out a detailed story about an astronaut named Commander Bob, complete with the type of cake and the year it happened.
And none of it would be true. In the AI world, this is called a hallucination. And while a story about mooncake is harmless, imagine asking an AI for medical advice or legal precedent. A confident but completely fabricated answer could be disastrous.
That's the core problem this paper is trying to solve. How do you build a lie detector for an AI? The paper is titled HalluField, Detecting LLM Hallucinations via Field-Theoretic Modeling, and it comes from a team at Los Alamos National Laboratory.
Now, that title sounds pretty intimidating. Field-Theoretic Modeling. You're probably thinking of complex physics equations. And you're not wrong, but the core idea is surprisingly intuitive. They're essentially asking, can we tell if an AI is lying by checking how stable its answer is?
Stability. Okay, what does that mean in this context? An answer is just a string of text. How can it be stable or unstable?
This is where the physics analogy comes in, and it's really clever. Imagine every possible answer an AI could give exists in sort of a energy landscape. Think of it like a hilly terrain. A good, factual, coherent answer is like a ball resting soundly at the bottom of a deep valley. It's in a stable, low-energy state. It's settled.
Okay, so a correct answer is a ball in a valley. What's a hallucination?
A hallucination is like a ball balanced precariously on the very top of a pointy hill. It might be there for a moment, but it's in a very unstable, high-energy state. The slightest nudge will send it rolling away.
A nudge. How do you nudge an AI's answer?
You turn up the heat, literally. Large language models, or LLMs, have a setting called temperature. A low temperature means the AI plays it safe, choosing the most probable next word every time. It's very predictable.
Like a straight-A student who always gives the textbook answer.
Exactly. But if you turn the temperature up, you introduce more randomness. The AI starts to explore other options, to be more creative. You're essentially telling it to consider less likely words. In our analogy, turning up the temperature is like gently shaking the entire landscape.
Ah, I see where this is going. If the ball is in the deep valley, the correct answer, and you shake the landscape a little, the ball will just wobble around and settle back down. It's stable.
Precisely. But what about the ball on top of the hill, the hallucination?
The slightest shake and it's gone. It'll roll off in a completely new direction. It's fundamentally unstable.
And that is the entire idea behind HalluField. The researchers take an answer from an AI. Then they ask the AI for the answer again, but with the temperature turned up slightly. They measure how much the AI's internal state changes. If the change is small and controlled, the original answer was likely factual and stable. If the change is massive and chaotic, it's a huge red flag that the original answer was a hallucination.
So it's not just about the final text, but about what's going on under the hood. The paper talks about free energy and entropy. How did those fit in?
These are the specific things they measure. In their physics model, free energy is basically a number that represents the stability and coherence of an answer. A low free energy is good, that's our ball in the valley. High free energy is bad, the ball on the hill.
And entropy, I remember that from science class. It's a measure of disorder or randomness, right?
That's it. In this context, entropy measures the AI's uncertainty. If the AI has high entropy, it means there are lots of different, plausible words it could choose next. If it has low entropy, it's very certain about the next word. HalluField looks at how both the free energy and the entropy of an answer change when you poke it by increasing the temperature.
So a hallucination is a state of high energy that, when poked, creates even more disorder and changes dramatically. A factual statement is a low energy state that, when poked, stays pretty much the same.
You've got it. It's a way to quantify the model's confidence and stability, not by asking it if it's sure, but by testing its conviction.
This sounds much better than some of the other methods I've heard about. Don't some approaches use another, bigger AI to check the first AI's work?
They do, and that can work, but it has two big problems. First, it's slow and expensive. You're running a second massive model just to fact-check the first one. Second, what if the fact-checker AI is also wrong? You're just adding another layer of potential failure.
But HalluField doesn't need a second AI.
Nope, it works directly on the outputs of the model you're already using. This makes it incredibly fast and efficient. The paper shows that on a per-query basis, it's orders of magnitude faster. We're talking fractions of a second versus almost a minute for some other methods.
Wow, so it's faster, more efficient, and how good is it at actually catching the hallucinations?
The results are very impressive. They tested it across a whole range of different LLMs and on several standard datasets for question answering. HalluField consistently achieved state-of-the-art or competitive performance. It's just really good at sniffing out these unstable, fabricated answers.
So to recap, LLMs sometimes lie, which is a huge problem. This paper, HalluField, introduces a new lie detector that's inspired by thermodynamics.
It treats a good answer like a stable, low-energy state, a ball in a valley. And it treats a hallucination like an unstable, high-energy state, a ball on a hill.
And to tell which is which, it gives the AI a little nudge by turning up its temperature setting and measures the resulting chaos. A big change means you've likely found a hallucination.
And because it's all self-contained, it's lightning fast and highly effective. It's a really elegant application of ideas from one field, physics, to solve a critical problem in another, artificial intelligence. It's a big step towards making the AI tools we use every day more reliable and trustworthy.